So it's time to start. It's 5 in the evening in Sweden, and I hope you are joining from all over the world. I heard we had 200 that have around 200 that have signed up for this talk. That's really great to hear. So welcome everyone to this exciting tinyML talk. My name is Johan Malm and I'm the moderator for today. I'm a machine learning engineer and head of products at Imagimob, where we develop tools for embedded AI. I'm also part of the committee putting together the Swedish tinyML local meetup that arranged these talks. And I'm very happy to announce today's speaker, Amir Aminifar, who will present edge machine learning for mobile health technologies. So will be really exciting to hear about. I will present our sponsors that make these talks possible, and where we have ARM, Deep Light, Edge Impulse, we have EMSA, Greenwave Technologies, Latent AI, HOTG, Maxim Integrated, Quexo, Qualcomm, Reality AI, SensiML, SynSense, and Syntient. Big thanks to them. I would also say that the tinyML Vision Challenge is still open and submissions are accepted until September 17th. So please submit your works. I should also mention that we had a successful tinyML EMEA conference 2021. There were 1,687 registered attendees. So that was really a successful event. And all of the videos are available on YouTube. And so please go there and check it out. I will present here that the local committee in Sweden that organizes these talks is composed of 4 people: Ali Balador, senior researcher at RISE, and it's myself, Magnus Melander, co-founder of Things, and Åke Wernerlind at Imagimob. So it's a pleasure to introduce Amir Aminifar, who is currently a WASP assistant professor in the Department of Electrical and Information Technology at Lund University in Sweden. He received his PhD degree from the Swedish National Computer Science Graduate School in Linköping, Sweden in 2016. And since then, he holds a scientist position at EPFL in Switzerland. He has been involved in several national and international projects, like the European Brain Project, for instance, and many others. He has a history of successful collaboration with industrial companies and medical partners, including General Motors, Texas Instruments, and so on. His research interests are centered around tinyML and IoT, mobile health, and wearable technologies. So it's a pleasure to introduce someone with such a solid background. So please, Amir.
All right, thanks very much, Johan, for the nice presentation. So yes, I would like to share with you our recent research results on edge machine learning today. And I'm going to focus mostly on the mobile health technologies and the medical domain. And of course, this is very connected to the tinyML community. So as Johan mentioned, my name is Amir Aminifar, and I'm currently with Lund University in Sweden. So let's start by talking about Internet of Things, or IoT. I'm sure a lot of you already are quite familiar with the Internet of Things concept. But for those of you who might hear this for the first time, the idea is that everything will be connected to the internet. And this creates a lot of opportunities, including autonomous driving, smart houses, and Industry 4. So now they talk about things basically in a technical and technical context, because essentially the idea is that you don't want to limit yourself to anything or anything. So the idea is that the most general term that you could use was in fact thing. And I'm going to talk about one application domain in this talk, and that's remote health monitoring. And this is actually a key enabler of preventive and precision medicine and healthcare, because you are able to monitor individuals or patients basically on a long-term basis, on a personalized basis, and in real time. And this gives you the possibility of detecting pathologies early on and perhaps preventing them. So I would like to focus mainly on one application that we have been working on for several years, and that's epilepsy. Epilepsy is basically a neurological disorder that affects more than 65 million people worldwide. And they have this group of patients, they have 40% higher premature mortality rate when you compare them against the corresponding healthy population. So epilepsy is usually manifested in terms of seizures, unprovoked seizures, unpredictable a lot of times. And these seizures are manifested as blanking out, fainting, losing consciousness, or maybe even violent body convulsions. So what is most important in this about epilepsy is that it is actually the second neurological cause of years of potential life lost. And this is due to the fact that there are seizure-related accidents, and also there is sudden unexpected death in epilepsy. So this is the epilepsy monitoring setting in the hospital. You have the patient here, and then you have, of course, a nurse, which is accessible, but not always sitting just beside you. So the patient is strapped to a lot of electrodes in brain, basically, and also the cardiac system. And you have here another video camera, which is also recording the physical activity of the patient. And so the electrodes here for monitoring the brain activities are also monitoring basically if there is a seizure going on in the brain or not. So everything will be transferred to this computer. You see the brain waves here and also the video of the patients. And this is used basically later on for cross-checking. And if there is an event during this monitoring process, which could be actually several days to several weeks, then it will be marked in this software. So, and after all of this, of course, an expert epileptologist or an EEG expert in Scandinavia will have to go through this data and mark and annotate the seizures and other events maybe. Of course, this is very important, and but it is within the hospital settings. Okay, so you cannot use this 24/7 at home and outside the hospital. But if you had the opportunity to monitor the patient in real time, basically it was quite useful. So first of all, it would improve the quality of life for these patients because, as I said, seizures are quite unpredictable. They are quite stressing and create anxiety for the patients. And if you have a way to monitor these seizures in real time, then it will reduce the stress and anxiety for the patients. And the second reason is that if you have a device that you can monitor the patients on 24/7, then you will have a lot of data. You can develop a better understanding of the disease, and in turn, diagnosis, prognosis, and treatment therapies. And last but not least, epilepsy actually has a huge socioeconomic burden on the society. This includes direct costs, such as medicine and hospitalization, but also indirect costs, because a lot of these patients, they cannot secure jobs. And if you have such a device or such a possibility of real-time monitoring, these patients could potentially secure jobs and lift this socioeconomic burden of the disease. But most importantly, if you have a real-time seizure detection possibility through, for example, wearable devices or IoT devices, you will be able to reduce the mortality rate. And this is mainly because you can notify the family members and emergency units for rescue early on and stop the mortality, basically. So let's look at the state of the art in real-time epilepsy monitoring. So we have VNS therapy, which is an advanced therapy. And this is basically an invasive therapy. It's only adjunctive. It means that it's not 100% curative. And it has side effects like any other invasive therapy, including potential risk of infection. More importantly, this is a procedure that is only recommended to a subset of patients and is also quite expensive. So it does not really solve all the problems in this domain. The second class of devices that we have are kind of intrusive and cumbersome. So for example, in this case, you have these epilepsy hats or caps. And as you see, this is not an easy thing to wear all the time 24/7, right? You have this port, which is quite cumbersome, and the wires, etc. But aside from being cumbersome and uncomfortable, the patients do not agree to wear devices that can be traced back to their to their health pathologies. So the devices have to be non-stigmatizing. And we have a new generation of wearables, such as bands and glasses that we have here and we have developed in our previous projects. So they are much less stigmatizing and they are much more comfortable, but they have very restricted form factors and sizes. And this in turn means that they have very limited resources to run algorithms. All right, now, Johan, if there is any burning question, I can take it so far. And
Yes, no, it's
okay, perfect. Everything is clear.
Continue. Yeah. So please, if you have questions, just post them.
All right. So usually for seizure detection, what you do is you use complex learning algorithms because they can learn patterns, complex patterns that are not possible to be learned using other techniques. And then, of course, on the other side, you have these resource constrained IoT devices like this e-glass system that we have. They are quite constrained in terms of computational power. For example, this one has only a tiny ARM core, and they are limited in terms of communication bandwidth. Bluetooth low energy most of the time is what they have. Very little memory storage. Here we have like 8 megabytes of memory, and very little battery budget. Also in here we have 150 milliamp hour, which is almost 1/10 or 1/20 of your mobile phones. And now the challenge is that you have these complex algorithms and you want to port them on these resource limited devices. And we have been working on this topic for quite some time now. And of course, we call it edge machine learning, which is, I mean, very connected to the tinyML community. And I'm going to explain this using a very simple example. I call this example the good, the bad, and the ugly. All right, so let's look at an example where we have a binary classification, and you have 2 classes. So class 1 is shown in green. Class 2 is shown in red. And then you have 2 feature sets. Feature set 1 is a simple feature set. Feature set 2 is a complex feature set in terms of computational power, energy consumption, however you want to interpret complexity. Now I talk about features, but you could imagine this is a simple neural network. This is a complex neural network, so no problem there. And let's say that the feature set 1 has complexity n, where n is the size of the input, like your brain signal, your EEG signal. Here we assume that is 1024. And feature set 2 has complexity n log n, which is 10,240 here in this case. And what we are interested in is to look at the quality of the classification at the same time as the complexity of the classification algorithm. Now here is a summary of what I just told you. The input size is n, 1024. Feature set 1 complexity is n, 1024. Feature set 2 is the complex one, n log n, 10,240. So let's look at one classifier, which is called ugly because it's low quality and high complexity. So this is the ugly classifier. So now in this case, this classifier sees everything this side of the line as green, everything here as red. But you see it makes some mistakes here. 3 points are misclassified here. And these 3 points are out of 50, so your classification accuracy will be 94%. So it will be 47/50. And then in terms of complexity, of course, it uses both feature sets. So feature set 1 and feature set 2. So it's a sum of the 2 complexities. So it's something around 11,000, let's say. So it's neither super accurate nor super light, right? So let's look at let's put it in this complexity accuracy graph that we have. So it actually ends up here. So it's 94% accuracy and something around 11,000 in terms of complexity. Okay, let's see another example. So let's look at this classifier. So this classifier sees everything this side as green and everything this side as red. So it makes also 3 mistakes. So the same accuracy that we had before, 47/50, 94%. But there is a difference. Since it's perpendicular to this axis, it does not use feature set 2. Okay, it only looks at the feature set 1. So the complexity is 1024, which is almost 10 times less complex than the other one. So it's not perfect quality. Let's say we call it low quality, but it's very low complexity. So it's quite nice. So let's look at where it ends up. So it actually ends up here. So it's 94% and 1024. So we in fact would like to be around here. So it's low complexity and very high quality. All right, so let's see a third classifier, which is, we call it high quality and medium complexity. And this is a combination of the two classifiers that we saw before. So we start by this with this low complexity classifier. So this is it. And we check if this classifier is confident or not. Now we have to define what means confident. So confident, if we are in this region, this classifier makes mistakes. So we are not confident in this region. But if we are in this region, the classifier doesn't make any mistakes. If we are in this region, the classifier doesn't make any mistakes. So in this gray box, the classifier is not confident. But if you're outside this gray box, you're done, perfect. Now, if you are inside this gray box, then we call the complex classifier. Okay, and you see it appears here. Now, inside this gray box, we use this complex classifier, and as you see within this box, this classifier works perfectly. So the red, this side is red and this side is green. Now, if we look at the expected complexity of this classifier, we see that E is the expected complexity, this one. We see that it has the complexity of the low-level classifier. We call it C1, low complexity classifier, plus the complexity of the high complexity classifier, but multiplied by a factor P. And P is the probability of calling this high complexity classifier, or equivalently, the probability that the low complexity classifier is not confident. Okay, let's look at the example that we had in terms of numbers. So let's look at accuracy for the moment. So we had this one, and then we said that if we are outside this, we use the low complexity classifier outside this gray box. So you see that everything here and everything here is correctly classified. Now, inside this box, you look at the blue one, which is a high complexity classifier, and you see that all inside this gray box, everything is also classified correctly. So you have 100% accuracy. Now, for complexity,
one question, Amir. I'm just a little bit. I wonder, how does this relate to a non-linear classifier? Your classifiers look very straight and linear, but is that just for visualization or conceptual purposes?
Exactly. I'm trying to make it really easy to understand and transfer the message, basically convey the message. But you're right. It can. I mean, the same concept can be applied to more complex classifiers.
Yeah, I see.
Because it might not be all.
Because here this would be solved, for instance, by polynomial or
Yes.
Yeah.
Exactly. But as you said, exactly. It can be solved by polynomial, but I'm just saying that this concept can be generalized, in fact, to as you said, to more complex cases that you really need to use these techniques to reduce the complexity. My point here is to basically simplify to the simplest possible dummy example that is easy for almost everybody to follow it. All right, so in terms of complexity, so we know the C1 and C2. They are 1024 and 10,240. Now we need to compute P. And what is P? P was the probability that the low complexity classifier was not confident. And this is basically the number of points in the gray area over the total number of points that we have. So now here is like 10 out of 50. So the P will be 0.2. And now you see that we just substitute P in this formula that we had here, and you get 3072. But what is important here is that, look here, that you have this big number, which was the complexity of the high complexity classifier, and it was multiplied by 0.2. So it was completely broken. And this is the beauty of the approach, basically. Now, let's map again. So we had this ugly case, low quality, high complexity. The bad case, low quality, but low complexity, better than the ugly, but still bad. And now we have in the middle a case where we have high quality and medium complexity. So it's not as good as this one in terms of complexity, but in terms of accuracy is quite good. And that is something quite relevant in terms of medical applications, because you really want to get to even sometimes couple of % more. Now, of course, we did this approach on a realistic case study, which was for monitoring heart attacks, and then we saw that you can improve the battery lifetime by 2.6 times, and you don't lose a lot in terms of performance. And of course, you can extend the idea to the case of distributed setting. So imagine now you have this older version of our glasses, which was a little bit more bulky and adjustable. That's why it's a bit more bulky. And then you have a low complexity classifier on this one. And then you run this low complexity classifier. If you are confident basically about your decision, perfect, you are done. If not, you can go to the cloud and run a very complex classifier, which is quite accurate. And in terms of analysis, it actually stays the same, the formula. The difference here is that C2 is not the complexity of the high complexity classifier, because it's now in the cloud. It has nothing to do with the sensor anymore, but it's basically the communication overhead of sending the data to the cloud, which might be also quite a lot in some cases. So it has to be taken into consideration, and it's important to break it with this probability P. Now, if you explore this distributed version of the approach, you actually might get to 3.6 times better battery lifetime. And again, you don't lose a lot in terms of machine learning performance. Now, this was a 2-level classifier that I mentioned, but in practice, you have several levels. So you have the edge sensor, run the low complexity classifier. If it's not confident, you go to you go basically to the fog level, or a local computer, if you wish, and check. I mean, you can run a classifier which is within the reach of these local computers or fog, or however you call it. And if it is confident, perfect, you go back to the edge sensor. If not confident, you can go to the cloud, and you can run the very, very complex classifier on the cloud platform. So it can be extended to several layers of classifiers. All right, so I actually talked so far about inference part of machine learning, but there are the machine learning part itself, the learning phase is also quite important. And we have been working recently on real-time federated learning in the context of epileptic seizure detection. And in that context,
we got a little question here about fog.
yes,
What is fog? Edge computing, or yeah, can you
yeah,
describe what you mean?
yeah. So I mean, the fog concept is quite foggy. So I just wrote fog here to show that, but I mean a local node maybe. But the fog has, I mean, I to be honest, fog has a very well-defined definition for people who are working at Ericsson or telecommunication. For me here, I just wanted to say that something that is not that is not that's kind of local. It's not the global cloud in another continent or something.
Yeah.
And it's hard to yeah.
Yeah, even the concept of edge is a little bit
Exactly.
vague. Some call mobile phone edge, and
Yes,
others go down to ARM M3, things like that. So it's
exactly.
not a strictly defined world.
Exactly. So edge, in fact, here I mean edge sensors, but you have also actually edge clouds, which are kind of edge of the cloud, like the cloud is so maybe, yeah, I mean, it's, as I said, so if you ask Ericsson research, they will tell you edge cloud. But if you in the IoT domain, a lot of people look at it as edge sensor. So there is as you said, it's not people understand different things from these two terms.
Yeah, and in the tinyML community, we usually say that tinyML should be machine learning running on a device that uses around 1 milliwatt or less than 1 milliwatt.
Exactly. And this is actually the case here. We have these low power, ultra low power devices, which are monitoring you, and you don't want to charge them every half an hour.
That's right.
Yeah. All right. So I have one last slide, which, as I mentioned, so we have been working, we have been talking so far about inference part of machine learning. Now, we have been also recently working on the real-time federated learning, which is focusing on the learning phase of machine learning. And in that case, you have basically a machine with an embedded GPU that is maybe close to your wearable, maybe on your mobile phone. In some kind of wearables, you can have also a tiny GPU or high performance platforms that are optimized for embedded system also on the wearables, such as Pulp, for example. But there is a machine that, let's assume that is closed or on your wearable, and it's communicating with the cloud. And the cloud, of course, is talking to many of such devices and trying to collaboratively learning basically a model that is high performance. And the idea here is that because of the privacy concerns and because of the overhead of the communication, you do not want to send the data of each patient to the cloud and do it in a centralized way. You would want to basically do this in a federated scheme. And of course, in the case of in our case with wearable devices in a real time, in the real time sense. And we actually demonstrated that this is possible to train neural networks in less than 2 hours and with 300-400 milliamp hour energy. And what is important here is that you don't need to do this in one shot. So you can do it, let's say 5 minutes every day, so you don't exhaust your battery. And so it seems to be in principle feasible, but I think I would say that this is a very, very recent paper that we had, and there is a lot to be done here. And with that, in fact, I would like to thank you all. And if you are looking for PhD position in Sweden, please do not hesitate to contact me. And I'm now actually available for answering if there is any questions.
Great. Very nice talk. It's very interesting to hear your research. So yes, contact Amir if you're eager to do research in Sweden, in the south of Sweden. And we're actually 100 participants, so no drop during the talk. Well done, Amir.
Oh, that's good news. Thank you all.
And I have a few questions here. So one is there any reliable wearable sensor to real-time monitor and detection of seizure? If yes, can you refer to any such project?
There is one wristband which is designed specifically for generalized tonic-clonic seizures, and that is commercialized, and it has all the medical approvals that you need to basically use such devices, and that is called Empatica. But as I said, this is basically focused on the generalized tonic-clonic seizures, which are around, I mean, it's a minority of seizures. It does not cover all types of seizures. And but in terms of research devices, there are quite a few. One of them is what we are designing, and we have been for several years, is this e-glass system, which is now in fact being evaluated by the university hospital in Switzerland. And there are also others which are around ear devices that try to basically do similar to our e-glass systems, basically. Yeah.
Yes. And related, can you mention about the sensor that is used for this? I'm guessing your project.
For this,
this is the word. This is not so well defined, but
okay.
Yeah, a bit unclear.
So the sensor, in fact, I mean, we designed almost, I mean, of course, the components, they were not designed from scratch, right? But we designed the sensor in the sense that the system ourselves, basically. And yeah, but as I said, the components are coming from, let's say, the manufacturer that are actually providing these components publicly.
Right.
And that's relevant also and important in the case of medical devices, because you have to validate everything, and
right.
if you start building everything from scratch, then that is going to make it harder for the validation.
Yes, definitely. Yes, so here we have another
guest.
Yeah. Thank you for the presentation. Can you share some background on why you picked seizure detection as your application? Do you mind sharing whether you have considered other health conditions for your tinyML project?
Yes, so I mean, seizure detection was one of the cases that, I mean, it's quite serious in terms of the fact that patients might fall down, they start bleeding, and you need to notify family members or rescue units as soon as possible. So that was quite nice case study in that sense. But we have been also looking into other case studies, such as heart attacks, for example, and sleep apnea, atrial fibrillation, And stress monitoring, we have been looking into it recently. But one of the nicest case studies that we had, and it was quite tight collaboration with the university hospitals, was this epilepsy that I cherry picked basically among my research work and tried to present it today.
Yeah, I think it's very interesting because I've been thinking for many years about it's a kind of very ad hoc right now and traditionally that you go to your local doctor, and it could be 10 years ago, and then suddenly he or she sees something that if you would have a sensor that could detect like every day, it could be everything from heart problems to that you just happen to go to your doctor at that point, and either you had luck and went to him the right day, or you had the bad luck and you were too late.
Yeah,
So,
absolutely. I
we
agree.
have all the tools. We have the sensors. Now we start to have the algorithms here as well, and so it's just to put it together, so to speak.
Yeah, exactly. I think that one of the main, I mean, it's kind of connected to this community, but one of the main points here is that if you closely collaborate with the medical faculty, in fact, that's quite relevant, because if you try to do these devices by yourself, I would say that's nice still, but the impact that you will have is probably limited, because I mean, eventually probably the super users or will be the medical faculties, I mean medical experts, that they propose these devices to their patients and to the individuals, and they have to approve these devices. So this tight collaboration is something that is quite necessary from the technical point of view. I think we have done, as you said, very well, and in terms of having sensors and algorithms are coming up now, but still I think to get it and then I mean I can tell you that from my collaboration, the medical community is quite let's say they have high expectation in terms of relevance of devices. So a lot of things that are being published now, maybe they considered not very relevant by the medical community, and they don't let's say encourage those devices. But I would say that this is one angle that the technical faculty has to has to push.
Yeah. And we see with the pandemic that sometimes it can be quick, even in the medical business.
Yeah.
So here is another one. Nice talk. Could you please elaborate about the use of ARM instead of other dev hardware platforms such as NVIDIA, Jetson, or TPUs?
Yes, so I mean, for the inference, so far we managed to run these tiny algorithms that we had on ARM Cortex, maybe the more powerful ones, and for the inference part, as I said. But when it comes to learning, we are now exploring, in fact, using Jetson Nano NVIDIA platforms. They are quite relevant. There is also some initiative to use other platforms such as Pulp, and that these platforms are mostly relevant when it comes to learning part, because that's the most complex in this context. But yeah, I mean, we are looking on this platform basically.
Right. Is tinyML helpful for anomaly detection using multimodal approach, voice plus voice?
Can you, in the last sentence, I didn't hear.
Perhaps they mean
they meant vision plus voice.
Vision plus voice.
Vision plus voice. Yeah, okay. Yeah.
Yeah, I actually, yeah, maybe. So we have been also working on multimodal, basically this kind of tinyML for multimodal biomedical variables. In the case of, for example, stress monitoring, you have multiple signals that you are monitoring, like cardiac and respiratory, electrodermal activity. So you have a bunch of signals that you are monitoring, and what you do is that you try to fuse them in a smart way that you don't spend all the energy, because sometimes this is a trivial case, you know, like if you have, like, I'm just giving an example, if you have like 120 heart rate, maybe you don't need to look at other signals to make a decision. But if it's on the border, maybe you need to look at several signals that can, if you put them together, you will extract information that is not possible otherwise. Okay. And I would say that the vision and audio is vision, voice, or audio. I think it can be one of those cases. And in terms of anomaly detection, we have a recent paper also for anomaly detection and this kind of two-level classifiers, this edge machine learning. Which if you are interested, you can contact me, or you will find it also on my Google Scholar page.
Here is someone saying that glasses could include an extension battery pack that could be kept in a pocket or on the person.
Yeah, could be. It is. I mean, there are a lot of ideas that you can charge them. Maybe, yeah. I mean, that is possible, I would say, but it is also possible for your mobile phones. But nobody does that.
Right.
It's the same problem.
I was wondering when the doctors, you showed how they label the events on their computer. Is that software developed by you, where they can label the events?
No, that's a software that is, I think, used in the hospital, and it developed since many years back. And it basically visualizes the signals and provides some help to annotate the data, because, as I said, it's like weeks of data that you have to go through, and EEG electrodes could be 20 signals each, and not so trivial to look at.
A lot of work to do manually?
I would say it's a lot of work. Of course, I've seen expert epileptologists that are doing it super quickly, and but still, I think it takes, for weeks, I think it takes at least maybe several hours or so. I'm just giving a number. I would take this number with a grain of salt. But they are doing it quite quickly. There might be some help with the software also, in terms of trying to filter the cases that are suspicious. We have been doing some of those algorithms that try to filter the parts that are potentially seizures, and that helps to reduce some time for the epileptologist.
Yeah. When sending data to fog or cloud, are those raw data? If so, how do you handle the security issue?
So in the case of what we have been doing, they are not the raw data, and it's important that this was a research paper, and is not violating the privacy or security of the patients. But as I said, is not the raw data. Is basically the updates that you try to make on the, so basically the gradients or the models that you have locally, you will share it with the cloud, and then in the cloud they will be averaged. But we are also working on the privacy issue, and to integrate this framework that we have with the privacy angle, and to reduce these concerns. But as I said, this paper was in the context of a research study, so it was not that sensitive to you know to send it to the cloud. Yeah,
I see. Yeah, because when you train the models, then you have data from yeah, not the people in the field, so to speak. Then you have other type of research data, or
yeah. So we actually had public data sets in this case.
yeah, okay, yeah,
okay. And as I said, this is not the raw data; it's just the updates, the gradients that are shared. So it is not much better, but since we have a public data set, I think it's not, it doesn't create a problem in this case.
Here is something. How is the response time of edge computing versus tinyML? I guess that's kind of synonyms in my mind.
I would say that they are at least very close, if not synonym, I would say.
Yeah.
But
and as we said before, where this edge is a little bit fuzzy, but usually the edge means where the edge of the network ends, and where computation is done locally without any help from the network.
Yeah. So I would say that in case of edge computing, or I mean, if you look at in terms of response time, you can take a look at one of our papers where I discussed about distributed machine learning. There we also look at the response time. It's based on models, because it's quite complex to capture the response time over the internet. You will get some kind of average, so that's kind of an estimation of the response time that you might get with the bandwidth that you have, depending on the communication infrastructure that you use.
Let's see here. Here is, thank you for a great presentation. Yeah. Microcontrollers runs programs with sequential execution. So does the same approach is running with tinyML on microcontrollers? What about interrupts? I guess that's more a technical question for firmware or embedded developers, perhaps. If you run with an or like an operating system, or on bare metal, or things like that. It can be done in different ways.
So we have actually RTOS, so real-time operating system. We do have interrupts, but you should realize that now we are talking about seconds and minutes. So an interrupt does not delay the process, at least a lot. So you can handle the interrupt quite quickly, and maybe you are delayed by maximum 1 second or so. And so you can, I mean, 1 second in terms of seizures is not, I mean, of course, it's better to do as soon as possible, but I would say that the 1 second sooner or later does not make a difference in this case.
Right. Yeah, it's a lot of questions. Maybe we have time for one more here.
Yeah.
How do you manage to read and write timing in the device's RAM for a real-time device? Is it not a bottleneck in this area?
Yeah, so that is an interesting question. I'm not sure if I understand very well the settings that we are talking about. But essentially, we calculate the average execution time of the first of all, the average execution time of this tinyML that we have for edge machine learning. But we also look at the battery lifetime of these devices and energy consumption. So you don't necessarily need to look at the time per se, but you could, I mean, in principle, connect battery and see when you run out of battery, right? And this is probably the ultimate test that you can make.
Right. Yeah, that's a good answer. Okay. And here again, we have the tinyML talk sponsors, and we'll just go through them a little bit more closely. The first is it's ARM, the software and hardware foundation for tinyML. Deep Light, we use AI to make other AI faster, smaller, and more power efficient. Edge Impulse, tinyML for all developers. EMSA, Visual Sense, the eye in IoT, Edge AI visual sensors. Green Waves Technologies, enabling the next generation of sensors and hearable products to process rich data with energy efficiency. HOTG, Distributed Infrastructure for tinyML apps. Latent AI, Adaptive AI for the intelligent edge. Maxime Integrated, the new Max 78,000 implements AI inferences at low energy levels, enabling complex audio and video inferencing to run on small batteries. Quexo, AutoML, automated machine learning platform that builds tinyML solutions for the edge using sensor data. Qualcomm, AI Research, a platform to scale AI across the industry. Reality AI, pre-built edge AI sensing modules plus tools to build your own. tinyML, build smart IoT sensor devices from data. SynSense builds sensing and inference hardware for ultra-low power, embedded mobile and edge devices. We design systems for real-time, always-on smart sensing for audio, vision, IMUs, biosignals, and more. Sentient is moving artificial intelligence and machine learning from the cloud to edge devices. So this is the last slide. I hope you can check out the sponsors web pages that I just went through. Very interesting companies, all of them. And yeah, this is the end, and I thank Amir again. Thank you very much for a very interesting talk.